Hello and welcome to lecture 29 of analog integrated circuit design. In the previous lecture, we looked at the differential pair as a means of taking the difference between two signals. This is an operation that is essential in realizing an op amp. Okay. In this lecture, what we will do is to analyze the various aspects of differential pair and also look at the simplest op amp that is possible using a differential pair. We want to take the difference between two signals Vp and Vm, and this is the structure we came up with. We thought of it as Vm being buffered by this transistor M2 and applied to the source of M1, whereas Vp is applied to the gate of M1, and the current in M1 of course depends on the difference between the gate and source voltages. Now the structure is symmetrical and you can instead think of Vp being buffered by M1 and applied to the source of M2. Okay. So the currents on the drains of both M1 and M2 will have information about Vp minus Vm. Okay. So you can load either of them. I will show a case where both sides are loaded by a resistance R. In this case what happens is that on the right side we will get CMRR by 2 Vp minus Vm, and on the left side we get CMRR by 2 Vm minus Vp. Okay. And the difference voltage between these two is CMRR Vp minus Vm. Okay. Now this node is called the tail node of the differential pair M1 M2, and this current source is called the tail current source, and that is equal to I0. We know that the bias current in the transistors will be I0 by 2 because of symmetry. Let us say each side is biased at some voltage V bias, and then we can apply Vp and Vm as increments to the two sides. Okay. Then when Vp and Vm are 0, you have I0 by 2 flowing through each side, and when Vp and Vm are applied, you will have these currents. Okay. Now this is a somewhat crude analysis. We assume that we have an ideal current source in the tail. Later we will add non-ideal features to that and see what happens. Okay. Now this is the small signal behavior. The small signal currents in M1 and M2 will be related to the difference voltage, and this is exactly the behavior we want in an op amp. In an op amp of course we want an integrating behavior. We would like this current to go into a capacitor. We will see how to arrange that. Okay. But for now we know that the currents through these are related to Gm times Vp minus Vm by 2. Okay. Now we also analyze the large signal behavior. We assume that Vp and Vm are equal and opposite voltages. Okay. And in such a case the currents in the two transistors would be something like that. Okay. This value is I0 by 2 and that is I0, this is 0 of course, and these voltages are now as Vd increases in the positive direction, what happens is that the VGS of M1 will be larger than the VGS of M2. So the current in M1 will be larger than the current in M2. Okay. And as Vd increases, this imbalance goes on increasing until a point where all of the tail current I0 flows into M1 and nothing flows into M2, and the voltage at which that happens is given by square root of 2 I0 by mu Cox WL. Okay. Now when you have a negative value of Vd, the opposite happens. The VGS in M2 will be more than the VGS in M1 and its current goes on increasing until it reaches a value of I0. Okay. Now around the value of Vd equal to 0, the variation in current with the input voltage will be a straight line and the slope will be Gm by 2. Okay. In each transistor the incremental current will be Gm by 2 times Vd, that is what we mean by the small signal current being Gm by 2 times Vp minus Vm. Okay. So, the current does increase in proportion to the input difference, of course as you expected over a small range, and beyond that the circuit becomes nonlinear, and in this part the circuit is saturated. Okay. Now, once you go beyond this point there is no response with Vd. By the way, these are the currents I1, I2 versus Vd, and this is the current I1 in transistor M1 and this is the current I2 in transistor M2. Okay. So, this is something to be kept in mind. Sometimes we need to know what is the linear range over which this differential pair operates. This is sometimes important for cases where we operate the differential pair not inside an op amp, but just by itself. Okay. And in an op amp also it is good to know when the current gets saturated, okay, because it is when this current gets saturated that we enter slewing. Now, we have a circuit like this, and the circuit itself is symmetrical. It is of course assumed that M1 and M2 are identical, right. So, M1 has a size W1 by L1 and M2 also has the same size W1 by L1. Okay. So, once this is assumed the circuit is symmetrical about that line. Okay. Now, before we go on to make this into an op amp, let us look at some properties of this circuit and see how to analyze it. Okay. Now, we want to do this both for large and small signals, specifically for small signals. Okay. That is, when we apply small signal increments to the two inputs, we want to see how things behave. Now, let us see a couple of cases. First of all, in this condition the circuit is completely symmetric and the voltages are also symmetrical. The same V bias is applied to each of these sides, and by symmetry it is obvious that this voltage and that voltage will be the same. Okay. In fact, you can assume them not to be the same and then come up with a contradiction and prove that they will indeed be the same. Okay. Now, let us say we apply equal increments to the two sides. Okay. I will call that VCM, that means it is a common mode increment, it is common to the two sides, and I will apply an equal increment. Again it is easy to see that this voltage and that voltage will also be equal to each other. Okay. In general, let us say we have a circuit which is completely symmetrical. Okay. Just to show the symmetry I will show it as the same network mirrored on the two sides, right. Now, this circuit will have a number of nodes and a number of nodes in that half as well, and let us say let us think of these two as inputs and apply equal voltages to the two sides. Okay. Now, by symmetry it is clear, so some of these could be tied to ground and there could be some components here as well, but by symmetry it is clear that, let me number these nodes 1, 2, 3, 1, 2, 3. The voltage here will be the same as the voltage there, the voltage here will be the same as the voltage there, and the voltage here will be the same as the voltage there. Okay. In our circuit we have only one such node, so the voltage here and there will be the same. Now, in that case we can safely connect the corresponding nodes together. Now, because they were at the same voltage, when you connect them like this, no current will flow through the wires connecting them, and so the circuit is not disturbed in any way. Okay. So, nothing changes due to this connection. So, what I could do is to do that. Now, what it does is to simplify the circuit significantly for the sake of analysis. Okay. Now, as you can see, the two resistors are in parallel and the two MOSFETs are in parallel. When we say two MOSFETs are in parallel, it means that all the corresponding terminals are connected to each other, that is the two gates are connected to each other, the two drains are connected to each other, and so are the sources and the bulks. Okay. So, let me redraw this circuit. Let me assume that the size of M1 and M2 was some W1 by L1. Now, I can combine the parallel resistors into a single resistor R by 2. I can combine the parallel MOS transistors into a single MOS transistor M12 with a width 2W1 and the same length L1, and this current remains I0. Okay. And this will be at V bias plus VCM. Now, as you can see, where we had pairs of components, we have a single component for the resistor and the MOS transistor, and the component along the center line of the circuit, in this case the current source, will remain as it is. Okay. So, roughly speaking, the number of components gets divided by half. Okay. Whatever is in pairs will be half, and whatever is along the center line will remain as it is. So, the number of components in the new circuit will be a little more than half of the original circuit. So, that means a corresponding simplification in analysis, okay, which we are going to exploit, and this is known as the common mode equivalent circuit. Okay. Now, this came just from the symmetry between two halves of the circuit. All we said was we have a symmetrical circuit, we apply equal inputs to the two sides. So, that means that the voltages in each half will be the same, they can be connected together. So, if we have a symmetric circuit like this, we can fold it up, connect the corresponding nodes, and come up with a simpler circuit with which we can analyze. Okay. And this is as I said, called the common mode half circuit. And also one thing to notice here is that the only property I used here is the symmetry of the circuit. I did not say anything about linearity, I did not use that. So, this common mode half circuit is valid for large signal increments in VCM as well as small signals, obviously. Okay. Now, we will not do the analysis right now, we will do the analysis a little later. Okay. Now, let us consider a different kind of input. Let us assume that the two inputs, the inputs to the two sides of a symmetrical circuit are equal and opposite. Okay. And this is known as antisymmetric excitation. Now, let me draw the small signal equivalent circuit of this. This is what we will have. The reason I drew the small signal equivalent circuit was the small signal equivalent circuit is by definition linear, and I am going to use that. Okay. So, let us imagine that we have two linear circuits which are exactly the same, that is it is a symmetrical circuit with some nodes connected between them, and there could be some common components as well. Okay. And let me assume one input on each side, there could be more. The important thing is that these are linear, and let us say I have antisymmetric excitation. What happens in this case? Because it is linear, I can apply superposition. First of all, I have only let us say plus Vd by 2 and 0. Okay. I have plus Vd by 2 and 0 on this side. I will have some voltages, okay, Vx, Vy, Vz along the nodes of the line of symmetry. Now, let us say I have 0 and Vd by 2. Now, because of the symmetry in the circuit, I will also have Vx, Vy and Vz along the line of symmetry, okay, on the nodes which lie on the line of symmetry. Now, let us say I instead have 0 and minus Vd by 2. What will happen? Because of linearity, where I had Vx earlier, I will have minus Vx and minus Vy here and minus Vz and so on. So, when I have both plus Vd by 2 and minus Vd by 2, what am I going to get? I will get the superposition of these two. Obviously, the superposition is 0. So, that means that in this case, in case of antisymmetric excitation, the voltages along the line of symmetry equal 0. Okay. So, this comes from a combination of linearity and symmetry. Symmetry guarantees that the response from each side is the same, and linearity guarantees that if you make one of the stimuluses opposite, one of the input voltages opposite of what it was, then the response will also be the negative of what it was, and if you sum up the two, you will obviously get 0 along the line of symmetry. Okay. Now, in the case of differential pair, there is this one node along the line of symmetry and that will be at 0. Okay. Now, earlier we determined this from conventional analysis, but in any fully symmetrical circuit with antisymmetric excitation, the nodes along the center line will have 0 volts. Okay. So, this can also be used to simplify the circuit. Now, so these voltages will be 0, 0 and 0. Now, again because of symmetry and linearity, if the voltage at a particular node here is some Vw, the voltage at the corresponding node there will be minus Vw. Okay. So, first of all, I do not have to analyze the full circuit, I will analyze it by setting these voltages to 0 and I analyze only one half of the circuit. Okay. Then I know that in the other half of the circuit, whatever voltages I have here can be negated and the solution obtained. Okay. So, whatever voltage is here, let me call that Vw, that will be minus Vw. So, what do I do with the differential half circuit? I will analyze only one half of the circuit. Okay. In this case, I will analyze, let us say, only this half. Now, how do I do that? This point corresponds to that point, it is at 0. This is anyway at small signal ground. I have R and GM times this voltage, of course, okay, and an input Vd by 2. Now, the solution here is trivial, the output is minus GMR by 2 times Vd, okay, and this is nothing but the common source amplifier. Okay. Now, what do I do with the differential circuit? I know that here I will have minus GMR by 2 times Vd, and from earlier arguments at this point I will have plus GMR by 2 times Vd, the exact opposite polarity. Okay. And the difference between these will be GMR times Vd. So, I can easily calculate that, and this node voltage will be at 0. Okay. It is not connected to ground, but in the differential circuit, because of symmetry of the circuit and antisymmetry of the excitation, that will be at 0. Okay. And this is known as the differential half circuit. Just like the common mode half circuit, it reduces the number of components and consequently makes the analysis easier. Okay. So, that is why we use that. These are very useful when you have a fully symmetric circuit and antisymmetric excitation or symmetric excitation. Now, right now the circuits that we make will not have this property, that the circuits will not be fully symmetrical. Okay. Later we will come to a class of circuits which for various very good reasons will be fully symmetrical, and the voltages applied will be either the same on two sides, that is symmetric excitation, or equal and opposite on the two sides, that is antisymmetric excitation. Okay. So, these analyses are extremely useful for those circuits. Okay. But because the differential pair by itself is symmetric, it is a good idea to know those things. Okay. Now, earlier we analyzed the differential pair using conventional nodal analysis. It is quite easy because the circuit itself is quite small, but it can be made even simpler, and the simplicity is particularly helpful when we go to bigger and bigger circuits. Okay. Now, let us come back to the common mode equivalent circuit. What did we have? I have V bias plus VCM, and this is M12, the combined transistor, which has a width of 2 times W1 and a length of L1. Okay. Now, it is very obvious in this that VCM has no effect on the output voltage, because this I naught, the current I naught has to flow into the source and also out of the drain. So, the voltage at this point will be VDD minus I naught R by 2 independently of the voltage VCM. Okay. So, this means that the circuit does not respond to common mode inputs. Okay. That is, the common mode gain of the differential pair is 0. Now, sometime back we discussed the common mode rejection ratio of an op amp. I said that the op amp should respond only to the difference voltage and not to individual voltages, okay, not to the average value of the voltage. And here it looks like we have exactly what we wanted. It responds to the difference voltage, and it does not respond to the common mode voltage at all. Okay. Now, of course, this is not true because we have assumed an ideal component here. The tail current source that we have used is ideal, and that is why it looks like it does not respond to the common mode input. We will replace it by a real current source and see what happens. Okay. Now, this current source is ideal. So, the current through the load resistance is also exactly I naught. Okay. This is a combined load resistance, by the way. Now, in reality the current source will not be ideal. Okay. It will have some output resistance R naught. What will happen in this case? As an increment VCM is applied, this node increases. Okay. In fact, if you think of the circuit with this as input and that as output, it is a source follower. The quiescent voltage here when VCM is 0 is V bias minus VGS of M12, which is the threshold voltage minus square root of 2 times I naught by 2. Okay. I can think of this as each transistor, that is each transistor of W1 by L1 carrying a current I naught by 2, or the combined transistor carrying a current of I naught. Either way, that is the quiescent voltage, and when we apply an increment VCM, there will be some increment in the source voltage, the voltage across the current source. Now, because this is a source follower, I will assume that the increment is equal to the input. Okay. We have earlier analyzed the source follower and showed that the increment is not exactly equal to the input, it is attenuated, and in case of the substrate being tied to the most negative potential, it is attenuated even more because of body effect. Okay. So, please take it as an exercise, calculate exactly what happens with the common mode input in this particular circuit. Okay. But I am not going to do that, I will just assume that the increment in the source is also VCM and go with the analysis. Okay. So, if the increment is VCM, this R naught, remember, is the incremental resistance of the current source. So, the total current flowing into the source of the transistor, this was I naught and it will change to I naught plus VCM by R naught. Okay. So, that is the total current, and similarly the quiescent output voltage was VDD minus I naught R by 2. Now, we have this incremental current also flowing into the load. So, we will have plus VCM by R naught times R by 2. Okay. So, the common mode input does have an effect on the output, it has a gain, the common mode gain is equal to VCM by R naught times R by 2. Okay. That is the common mode output voltage, sorry, the gain will be that divided by VCM. So, the common mode gain is R by 2 R naught. Okay. So, a quick summary of the differential pair is that the differential gain, this means that the differential output the difference between these two divided by the difference between those two. Okay. When I apply a differential input only is given by CMRR. Okay. I look at the difference between the two output voltages and divide it by the difference between the input voltages, this is the gain. The common mode gain, which refers to the output common mode voltage, which is VOP plus VOM by 2. Okay. Remember, when I apply the same input to the two sides, when I apply a common mode input, the two outputs will also be the same as each other. Okay. So, the average value is the same as the individual output voltages. And this is with common mode input, it is measured with a common mode input, and the common mode rejection ratio, which is the ratio of the differential gain divided by the common mode gain, let me call these AD and ACM, equals GMR divided by R by 2 R naught, which is equal to 2 times GM times R naught. You can see that it predominantly depends on the tail current source, the output resistance of the tail current source. So, if you want to improve the common mode resistance ratio, you have to improve the tail current source, you have to increase its internal resistance. Okay. Now, this is DC analysis. Now, in many cases the AC common mode gain is also important, the AC common mode rejection ratio is important. In that case, the formula will be exactly the same, except that the resistance R naught is replaced by an AC impedance Z naught. Okay. So, you will have 2 times GM times absolute value of Z naught, and you have to improve the impedance of the current source at all frequencies if you want to improve the common mode rejection ratio at that frequency. Okay. Now, why were we thinking of common mode and differential inputs? I have explained this before. So, any signal, let us say if we have a pair of signals, instead of thinking of independent signals Vp and Vm, we can think of them as their average value plus half the difference and minus half the difference. Okay. Vp plus Vm by 2 is the average voltage or the common mode voltage, and Vp minus Vm is the differential voltage. We prefer to think of this way instead of thinking Vp and Vm directly, because in a lot of cases we want something to happen to the differential signal. Usually we want our circuits to respond very well to the differential signal and not respond at all to the common mode signal. Okay. So, because of this we separate the signals into differential and common mode. There are also alternative cases where we want some part of the circuit to respond only to the common mode and not respond to the differential. Okay. So, that is why mathematically the two representations are equivalent. You can represent a pair of voltages as Vp and Vm or their average and difference values. We prefer to think of them in terms of the average, that is common mode voltage and the differential voltage, because functionally they make more sense. Okay. So, we have a symmetrical circuit with a symmetrical load. Now, this is not yet an op amp, we have to make an op amp out of it, but this is a circuit that we came up with along the way to synthesizing something that takes the difference between voltages, and this is a very widely used circuit. So, that is why we analyzed it. Now, we will try and make an op amp out of this circuit. Okay. Now, let us say I have some bias voltage on the two sides and equal and opposite Vd by 2 on the two sides. Okay. Now, what is my op amp circuit? I have some transconductor that converts the input difference into a current and passes that through a capacitor C. Okay. Now, I know that whatever transconductance I make will have some resistance R naught, and I would like to maximize this. Okay. Now, if we compare this to the circuit that we do have a circuit that takes the difference, and the incremental current in the transistors is related to the difference in the voltage. Okay. Now, the circuit that we have also has an output resistance, and also the way we have drawn the circuit, it is symmetrical. We want only one output. So, we will just take one of the outputs and ignore the other one, that is entirely possible. Okay. So, let us say I take the output only from this side, and I could pass this through a capacitor. Okay. Now, I also want the output resistance looking in there to be very large. Now, what is that output resistance going to be? Let us assume that the transistors have no output resistance at all, that is they have GDS equal to 0 or RDS equal to infinity. Now, when you have 0 incremental voltage here, the transistors simply become an open circuit, and the resistance looking in here will be just this resistance R. Okay. It can also be thought of in another way. The DC gain of this circuit is Gm times R naught, the DC gain of that circuit from this difference input to the output, that is, let me call this V out by Vd will be GMR divided by 2. Okay. Now, we know that this can only be a modest number, because this is the gain of the common source amplifier, and this is only a rather modest number that we can get when our supply voltages are limited. Okay. To increase this gain value, we have to go on increasing the value of R, but if we increase the value of R, the DC voltage drop across it I naught R by 2 will go on increasing. So, that means that we have to increase the supply voltage as well, okay, to keep all the transistors in saturation region. Now, this is prohibitively expensive, it is just not allowed in real circuits, your supply will be limited to some extent. Okay. So, this is not a way of increasing the DC gain, we cannot make better op amps using that kind of technique. What we have to do is to substitute the resistance with something else that will look like a very high resistance, but will not demand as much a voltage drop. Okay. We know that an active load, that is using a MOS transistor as a current source, is a very common way of obtaining a very high incremental resistance while keeping the voltage drop across it to a limited value. Okay. So, if we have a transistor in saturation region, so let us say I have to connect a resistance to VDD, this is the situation I have in my differential pair. Now, this can be equivalently done by connecting a PMOS transistor to VDD and ensuring that this is in saturation region. Okay. If it is in saturation region, what does this look like? It looks like an equivalent resistance RDS, and we know that in saturation region this RDS is rather high. From the output characteristics of the MOS transistor, which are very flat in saturation region, we know that the GDS is very low or RDS is very high. Okay. And this is a very common way of simulating a very high incremental resistance, and the voltage drop across this is not related to the resistance value, but it is related to VGS minus VT of the transistor. Okay. It is the VGS minus VT of the transistor. So, depending on what VGS you bias this with, you can have a fairly limited value. Okay. So, let me start again with my differential pair. R and R. Now, this side is not being used, okay, the left side is not being used. I could connect it to anything I wanted, and I take my output from here, and what I want to do is to replace this by a PMOS transistor in saturation region. Okay. Now, clearly the PMOS transistor in saturation region must carry a current of I naught by 2, and a convenient way of biasing it could be from a current mirror. Where this is I naught by 2. Okay. Now, let us assume that these transistors are in saturation region and go with the analysis. Now, this is a way of doing it, but this is also looking particularly wasteful, because we have an extra bias branch of I naught by 2, and we also have a current of I naught in the tail of the differential pair M1 M2. Okay. So, what we can do instead, given that the current in transistor M1 is not used at all, and we also know that in quiescent condition the current in M1 is the same as current in M2, and it is equal to I naught by 2. Okay. So, what I can do is do that. Okay. So, in the quiescent condition, because of symmetry, we will examine this in little more detail. So, the current here will be I naught by 2 and the current there will be I naught by 2. Okay. So, this will get mirrored in the current mirror, let me call these M3 and M4, and here also we will have I naught by 2. We will assume all transistors are in saturation. Then what happens is, first of all, if you do assume that the transistors have 0 GDS, then the incremental resistance looking into the differential pair, okay, is infinity, because you see that all transistors will have infinite RDS and this is also infinity. Okay. And that will be the ideal case when we have a transconductance with infinite output resistance and the op amp behaves like an ideal integrator. In reality, the transistors will have some GDS, and we have to analyze the effect of that we are going to do soon. Okay. But this is a topology that can be used, because it gives a very high output resistance, as high as the value of GDS can possibly be, and it converts the input difference voltage into a current and drives it out. Okay. Now, I said that the currents here will be similar to the currents earlier. Okay. That is something that we still have to examine, right. Now, it turns out that when RDS values are infinity, that is true, Okay, the current in each of these transistors will be simply equal to Gm times Vd by 2. That I leave it as an exercise to you to verify by circuit analysis. When RDS values are infinity, you please find out the currents in each of these transistors. Okay. Now, when the RDSs are not infinity or GDS values are not 0, the analysis turns out to be a little more tricky and we have to be careful. Okay. And particularly careful because the answer looks similar to what you get when you assume GDS equal to infinity, but some of the things are different. Okay. So, we will spend some time analyzing this circuit both for the voltage gain and the output resistance and so on. And also one important thing to note here is that the symmetry has been destroyed. Earlier we said that when you have a symmetrical circuit with anti-symmetric excitation, we can do the analysis very easily. Okay. That was because of linearity and superposition, the voltages along the center line was 0. Now, this circuit is not symmetrical. Okay. The PMOS side of it, M3 and M4 are not connected symmetrically. So, we have to be a lot more careful and we can't apply the concept of differential half circuit directly to this particular circuit. Okay. As I have mentioned many times, M1 is identical to M2 and M3 is identical to M4. Okay. Instead of Vp and Vm, I will show it as a bias voltage plus differential or common mode increments. Now, the transistors will have some GDS values. Okay. In reality, they will be there and we have to include that in the analysis, and throwing all the equations together and analyzing it is not very useful. We have to get some intuition as well. So, that is what we will do. Now, first let us start with the quiescent condition, that is we have only a V bias applied to the two sides and we have a tail current I naught and the transistors are exactly identical. In this case, we do not assume any mismatch, we assume that the transistors are perfectly matched. Now, the question is, what is the output voltage going to be? This is the output of my differential pair transconductor. So, what is this V out? So, again as usual, please pause the lecture at this point and try to reason it out, and you can assume some value of GDS for the transistors, and M1 and M2 can be considered identical as are M3 and M4. Okay. Now, if you go through the reasoning correctly, you will find that this V out under the quiescent condition will be exactly the same as that. Okay. Let me call this Vd3. So, V out will be equal to Vd3. Now, how do we know? The easiest way to prove this is by assuming that, let us say V out is more than Vd3. Now, keep in mind that under the quiescent condition, Vgs1 and Vgs2 are equal to each other and Vgs3 and Vgs4 are equal to each other. Okay. Now, if two identical transistors have the same Vgs and if their currents are different, the only way for that to happen is for the VDSs to be different. That is, if two transistors have the same Vgs and if one of them has a larger VDS, it will also have the larger current. Okay. Now, let us assume that V out is more than Vd3 and see what happens. So, if V out is more than Vd3 and you think of M1 and M2, this implies that VDS2 is more than VDS1, which in turn implies that the current in transistor M2 is more than the current in transistor M1. Now, if you look at the same thing for M3 and M4, the same condition implies that VSD 3 is more than VSD 4, which implies that I 1 is more than I 2. So, clearly this is a contradiction, and the only consistent solution is to have V out equals V D 3. Okay. So, when the circuit is perfectly symmetrical, this will be the case, and that also means that all transistors will be in saturation. Okay. Assuming that V bias is small enough, it is very clear that M4 will be in saturation, because the gate voltage of M3 is the same as drain voltage of M3, and the drain voltage of M4 is the same. Now, V bias, let us assume, is small enough, so that M1 and M2 are also in saturation region. Okay. So, this tells you something about the quiescent condition, the V out will be equal to V D 3. Okay. Now, what this means is that let us say I connect a voltage source here, which is equal to V D 3. What is V D 3? V D 3 is V D D minus V S G 3 at a current of I 0 by 2. I will use this notation. What this means is the V S G of transistor M3 at a current of I 0 by 2. Okay. I do not want to keep on writing V T plus square root of I by mu Cox etc. every time. So, I will use this notation. If I connect a voltage source of that value to the output, nothing changes in the circuit, and the current here will be 0. Okay. Because the current balance is between M2 and M4 and M1 and M3, and nothing flows into the source. Okay. But the output is now incrementally short circuited, and we will exploit this fact to do further analysis of our differential pair. Okay. So, what we have done is to look at ways of analysis of a fully symmetrical circuit with symmetric and anti-symmetric excitation, that gives you say common mode and differential half circuit concepts. And we also came up with a circuit for obtaining a high gain while taking the difference between the input voltages, and that is the differential pair with the active current mirror load. But this circuit is not symmetrical, and if you throw every aspect of the circuit into the analysis, we will get no intuition at all. So, we will proceed step by step. First, we have proved that the operating point by itself will be identical, and this also means that I can connect an output voltage of some value which I know, that is equal to V D 3, and nothing will change in the circuit. Okay. Using these, we will analyze the differential pair in more detail in the next lecture. Now, just a quick summary of what we did today. We will have identical voltages in the two halves of the circuit. So, this means that basically the two halves can be folded on top of each other. So, this means that all conductances will be doubled, all MOSFET widths will be doubled, all capacitances will be doubled. Okay. The capacitances which are repeated on both sides, the MOSFETs which are repeated on both sides, and so on. Okay. And similarly, the inductances will become half, and resistances will become half, and so on. These are the components in the two halves, and the components along the line of symmetry these are not changed. Okay. And this gives us what is known as the common mode half circuit which is considerably simpler than the original circuit and also considerably easier to analyze. Okay. Now, let us say we have a symmetric circuit with anti symmetric excitation. So, if the circuit is linear, which could be a linear circuit by itself or the small signal equivalent of a nonlinear circuit, the voltages along the line of symmetry and the voltages in each half are antisymmetric. This gives you the differential half circuit. So, you analyze only half the circuit by tying all the voltages along the line of symmetry to 0. Okay. Very useful technique when you have fully symmetrical circuits. We will continue from this in the next lecture.